All right. Hi, everyone. Want to first thank everyone for taking time to join us today on our developer community meeting. Our agenda will be brief. We will start off with just a brief information about our developer community meeting. We will talk a little bit about recently launched, and then we'll allow Sia to talk a little bit more about or go into depth about our training GPT-J on a single CS-2. All right, so for everyone here, I guess you get first chance at hearing about this news, but we've recently launched our discourse forum. So if you go to discourse.cerebras.net, you'll be able to register and access our forum. We hope that you use this site for asking questions, answering other community members' questions, sharing your work to receive early feedback, and then also providing us with feedback, not just on Discourse or our website, but our software or hardware. And finally, also having access to our latest news that we'll pin at the top of the forum site. So hopefully everyone here signs up for Discourse, and it provides you guys a lot of benefit. All right, what's new with our software release 1.4? So as I'm sure you're aware, we have announced that on a single CS2, you can train multi-billion parameter NLP models like the GPT family, which we'll be discussing in today's developer community meeting. In addition to that, for PyTorch support, we've made performance improvements for small and medium-sized models through our multi-replica and our variable tensor shape support. For TensorFlow, we've also added multi-replica mode and variable sequence length for the T5 model in pipeline execution mode. And if you'd like to learn more about this, please visit our website, cerebras.net. Additionally, you can check out our reference implementations in our GitHub, which is on the bottom right of this slide. So yeah, without further ado, Sia, I'll let you take over.
Okay. So welcome everyone. Today I'll give you sort of a brief introduction to GPT-J and how you can train it on the CS2 system. Okay. But before we jump into the actual training on the CS2 system, let's talk a little bit about training large models on GPUs today and the challenges that you face when you try to do so. There are a couple of techniques to scaling out models to be trained on large clusters of GPU. The first and the most familiar and the easiest one is the data parallel model, where you basically have a copy of your network across multiple devices, and then you aggregate gradients and distribute weights. When you parallelize your work with this model, the limitation is that the model needs to fit each GPU. The next step, or another way of distributing the work, is to spread the layers of the model across multiple GPUs. And this has the benefit that now you can fit larger models, but there is a communication overhead associated with transporting the activations across multiple GPUs. And also, so in order to sort of utilize the GPUs fully, you need to use larger batch sizes. And another method yet to distribute the work is to use the tensor parallel model, and that in that way you sort of distribute each layer across multiple GPUs. Here you need a very low latency, high bandwidth communication in order to run this parallelization efficiently. And usually you need to be mindful of this mode of parameterization when you're designing your model architecture. And in practice, to train large models, you have to use a mixture of all these three methods. And there is really no one-size-fits-all way to determine what's the best way to do this parallelization for different model architectures. And usually, like big companies that train these big, large models have teams dedicated to determining this workload distribution strategy for each model. And there's sort of all these complexity really arises from the compute and memory being highly tied together, which is sort of the nature of running neural networks in some sense. And so here, my colleague has done a little bit of research and put together this graphic, which I think is pretty interesting. So the graphic shows you what parallelization methods different teams have been using in order to distribute their workload. The gray bars correspond to the data parallel. I should mention that the y-axis is the log of the number of devices used. So the gray bars show the number of devices used for data parallel. The blue bars are the number of devices for tensor parallel, and the green bars are the number of devices that are used for model pipeline parallel. And we can see for smaller models, people start with using data parallel method, which is the easiest one to implement. Past a certain size, they switch over to using tensor parallel. And you can see as models scale up, the number of nodes used for tensor parallel doesn't scale up that much. That is because employing tensor parallelism requires you to have really high communication bandwidth and low latency. So it's usually implemented within a single box. And as models scale up, the last technique that kicked in was the pipeline parallelism method. And so in order to sort of implement this type of parallelism, you can see that it is highly dependent on the model architecture. The way you implement this, mix these, sort of hit the magic ratios for all these, for a mixture of all these types of parallelism. It's highly dependent on the model architecture, and it's highly dependent on the characteristics of the cluster, the GPUs, how many GPUs per box, how many boxes, and so on. And the way we address this, we introduced a feature recently called wave streaming, and it basically disaggregates compute and parameter storage. So the way it works for large models, in order to do a forward pass, the weights are for each layer are streamed layer by layer into the wave streaming, into the wafer scale engine. So if the weights for the first layer are streamed in, we do a forward pass, and then we stream in the weights for the second layer and do the forward pass for that layer. And during the backward pass, we streaming the weights in the reverse order and compute the gradients and stream the gradients back out to the external memory where the optimizer operates and takes the optimization step. The benefit of this model is that we can scale up memory. We can sort of add more servers that have larger and larger memory for larger models, and we can scale up the training speed independently of memory by adding more CS2 systems that can basically scale out your training in a data parallel fashion. And the nice thing about this is we can, do you have a question? Oh.
Yes, yeah, there's a question in the chat.
Yeah.
Is the split between parallelism approaches to achieve better performance or accuracy? Good question.
It's a great question, and it's a mixture of both. Actually, that reminds me that I sort of missed a point on this plot. So if we look at the yellow and blue curves on this plot, the yellow curve indicates the batch sizes that were used to train the models. And the blue curves are what they call the critical batch size, which is the optimal batch size that has the best convergence characteristics. And we see that in most cases, the teams had to increase the batch size to get good hardware utilization beyond what's the optimal batch size. So I guess it's then becomes sort of a mixture of both. So you want to get good performance by good utilization by increasing the batch size, but that sort of doesn't have great convergence characteristics. So there's sort of two things that you're trying to optimize at the same time.
I have a quick question about the streaming process. So in the streaming process, each layer streams to different CS2s, for example, if you have multiple CS2, but basically it's a replication of the model.
Yes, so yes, so when we have multiple CS2, we scale up in a data parallel fashion.
Okay, you can do this basically because each CS2 has large enough memory compared, for example, to GPU. Is that correct?
So the reason is that we are loading each layer so each layer at a time. So the CS2 has enough memory to sort of accommodate one layer.
Okay, and in principle, you can do that for GPUs also. You can stream one layer at a time as long as each GPU has enough memory for a single layer.
You may be able to do so. I'm not sure. I'm not sure if it's definitely not something that people do.
Okay, thank you.
Yeah.
And you have the problem of the amount of SRAM available on the two devices, the relative amount of SRAM on the two devices, right? That limits the maximum layer size.
Yeah, I guess that's maybe a critical point.
Yeah, so one of the benefits of the wafer scale engine is that it has thousands of processing elements, and each one has its own memory, and so the memory is distributed across the wafer. I think that's why it makes sense to implement this wave streaming model. Okay, is there an overhead of streaming in and out the waves? Do we? So as far as I understand, it's the way it works is that it continuously cycling sort of streaming waves to the wafer, so to minimize bubbles. So the wafer is not sort of waiting on the waves is constantly busy with running some kind of compute, but I'm not too familiar with the details.
I'll post a couple of links for those that want to dive deeper into the way that the slow bits are hidden behind the fast bits, are hidden behind the slow bits. The other way around.
Okay. So, and sort of another benefit of this model is that we don't need to change the code or change the architecture to use this to sort of use this waste streaming model. So the same code can be used for running the model on a single CS2 in the pipeline mode, or it could be used on running a single CS2 in waste streaming mode, or it could be used on a cluster of CS2s. And yeah, so all of this is more or less opaque to the developer. So so today I'm going to talk about training GPT-J. Let's take a quick look at what the GPT-J architecture looks like. So it's an autoregressive model similar to the older GPT-J architectures. In one way that it deviates from the GPT-J architecture is that in the decoder blocks, the feed-forward layer and the attention layer operate in parallel instead of being one after the other. This was done to make distributing the compute across multiple GPUs easier. So in our case, we don't really care about this change. We don't have to do it, but we have implemented GPT-J like this way to make sure that we can use the publicly available checkpoints. And can you guys hear me?
Yeah, we had a slight, I think we had a slight glitch in Zoom there for a lot of people.
Oh,
Maybe back up to the start of this slide.
okay. Can I go now?
Yes, sorry about that.
Okay, no worries. So GPT-J is similar to the GPT architecture in that it's an autoregressive model. And the only way that it differs, so one way that it differs from the GPT architecture is that the decoder block is operates, so runs the feed forward and the mask multi-head attention in parallel instead of one after the other. This was done to optimize performance across multiple GPUs. And so we don't really care about this architecture change. We're not constrained by it. But we have implemented GPT-J in our Model Zoo implementation to match that of the sort of original implementation, so we can use the publicly available checkpoints. Another way that GPT-J differs from older GPT models is that it uses rotary positional embeddings that have been shown to be better suited for longer sequences of text. It also uses dense attention as opposed to GPT-3, which use some form of sparse attention. Okay. So why did we choose GPT-J as sort of our first large model to implement? First, it is small enough to still be practical to be deployed for inference. The second is that it is large enough so that it is still cumbersome to train it in a distributed fashion across multiple GPUs. And the third point is that it surpasses out-of-the-box GPT-3 when it is fine-tuned on the target domain. It has publicly available checkpoints, and it's pretty versatile, so it can be used for a variety of tasks like summarization, question answering, and auto-completion. So let's take a tour of the code base. This repository that you see here is a public implementation of a couple of models that we have made public so you guys can sort of browse them at your own leisure. But today we're gonna take a look at the GPT-J implementation. We generally organize our implementations for all different models in a similar fashion. There are a couple of files that exist in all of them. The first one is the run.py file. This is the main Python scripts that you use to launch a training job. The utils.py is a couple of helper functions. Models.py is basically implements the model and its loss operations. And data.py has data preprocessors and sort of data feeders to the model. And we also have a configs folder for each model where we store YAML files. So these YAML files are basically the way we specify different hyperparameters and for the model, and we configure the runs. There are a couple of fields in the YAML file. So we have the training input, which specifies which data processor to use, specifies the path to the training data, vocab size, maximum sequence length, and different things about the input. We have the model field, which has different hyperparameters about the model. So like the embedding size, dropout rate, hidden size, filter sizes, activation function, and so on. So in order to change the model, it's basically you can change these numbers and run different experiments. The way we sort of recommend doing it is to create different copies of this YAML file with the changes, and sort of it's a good way of keeping track of different experiments that you do. We also have hyperparameters for the optimizer, the optimizer type, weight decay, learning rate schedule, and so on. And the run config field specifies things like the maximum number of steps that we want to train the model for, and the frequency of saving summaries for TensorFlow and saving checkpoints. So training in base streaming mode, the first thing that needs to be done today is we need to first put the CS2 system into the base streaming mode. And this step will be eliminated in the future. So for now, we basically change the mode by putting the system into the standby mode. So either you or someone who has access to the admin panel on the CS2 basically can log in. We can put the system into standby mode by running system standby. It usually takes 10 to 15 minutes. Then you run config exec mode setup. This basically gives you a multiple choice menu where you select either wave streaming or pipeline. In this case, you pick wave streaming. And then you run system activate. It all takes, again, like 10 to 15 minutes for the system to be activated. After that's done, when you run config exec mode, you'll see that it says wave streaming. And again, this step will be eliminated in the near future releases. In order to actually run a training job, so as you may know, the CS2 system is like a network attached accelerator, which is attached to a cluster of 8 or 9 nodes, which are normal CPU nodes. And the whole cluster of those nodes is managed by the Slurm job scheduler. So in order to run a training job, we provide a bash script which we call CS-run_WSE. This is a helper script that basically constructs that command for Slurm to run to submit a training job with sort of the right parameters and configurations. So the command to launch a training job for GPT-J looks like this. We specify the total number of nodes. We specify the single task nodes. This should be 2. Python_WS is basically Python with some additional modules to enable wave streaming. And then we basically run the run.py command. The run.py script takes the parameters, the YAML file that we talked about. We pass in the mode, which could be eval or train. In this case, it's train. We pass the path to where we want the artifacts of the training be saved. We have to pass the IP address of the CS2 machine. And if we are training from a pre-train checkpoint, we can pass in the path to that checkpoint. Once we launch, run that command, we'll see that the job has been queued to Slurm, and here the job has been allocated. Resources have been allocated for the job. And the first step is that the model starts compiling. This could take a few minutes. And once the model compiles, it actually starts running training on the wafer scale engine, on the CS2 system, and you would see loss and like printouts from the model, the same as you would have seen if you ran on like CPU or GPU. And yeah, once the run finishes, you get your run artifacts in the model directory that we specified in the CS run command. The artifacts include logs from different processes that support wave streaming. These are helpful for debugging. We have event files for TensorBoard, and we have checkpoints of the model. So this is just an ls command of a run that I did a couple of days ago. So we see the events file. So this can be passed on to TensorBoard, so you can sort of monitor how the training is going live. We have the checkpoints. It also saves a copy of your YAML file here, so you sort of can sort of tie back the parameters of the YAML file to the run. Oh, I have a question. Okay, so can you? I'm not sure about the first question. I don't think so. So, you know, so to cap the utilization of the CS2, is that?
I'm not sure we've ever been asked that one before. That'd be a great
Yes.
discourse question.
Yeah, usually everyone.
Mamal, could you jump on and tell us a bit more?
Sorry, I mean, I just joined the company yesterday, so I was just wondering if you can cap the utilization. I'm not sure, like, as in like percentage of use, if there's like more than one job running.
Oh, okay. Yes, so Slurm jobs usually require a number of nodes to be available. So if we submit multiple jobs that are asking for the same resources, they have to remain in the queue until like the current job has finished running.
Okay, sure. Okay.
And can you log in directly to CS2? So the admin interface that I showed earlier is basically as close to logging in directly to the CS2 as I'm aware of. So basically this enables you to check the status of the system, check the version of the software that's installed, and so on.
Okay,
And yeah.
thank you.
And another great question for you, Sia, from Dennis.
Mm-hmm. Is it possible to reproduce wave streaming in CS container running on GPU or CPU? So if you are trying to run on GPU or CPU, you don't need to use our container, but the code should be fully compatible with running on GPU or CPU. So as long as, so for GPUs, as long as you figure out the distribution of the workload, because our wave streaming code is identical to the code that you would write to run on a single GPU. But you wouldn't need our container.
And that's a really important point, right?
Yes, yeah.
That's kind of the point of this, that you don't need to recode for multiple devices.
Yeah. So, and this is our log. So we talked about the artifacts. Now, another sort of interesting or very useful property of wave streaming is that because we are loading things one layer at a time, we free up a lot of memory, so we can run larger sequences. And usually, like off-the-shelf GPT-J or other transformer models that you find, they're trained on maximum sequence lengths that are somewhere between 512 to 2048. And that's about like 1,000 or like max 1,500 words maximum. And there are a lot of useful tasks that require a larger context. Like summarization is like one task. Usually when you want to summarize a document, it's much longer than 1,000 words. And since dense attention has quadratic complexity, a lot of methods have been introduced to sort of bring down that complexity, but they all make compromises one way or another. With the CS2 in the wave streaming mode, we can run GPT-J up to 30K tokens today with just a minor modification. So we basically have to pre-process our data if we are feeding TF records so that the samples are 30K long. And we need to, the only other change is that we need to make sure the positional embedding generator knows that our sequences are 30K long. So, and with these like two simple changes, now we can train on much larger sequences. If we think back about training on GPUs, scaling your sequence by this much will most likely require you to rethink your whole distribution strategy because those attention matrices will be much, much larger. But it's pretty easy to do in wave streaming with CS2. Yes, so Rebecca says we like to hear from folks that have a use case for 30K sequence length. Currently, we are working on a summarization project. I'm sure, like and some biomedical applications. There are plenty of things that can make use of processing these long sequences. Going back, so here are a couple of resources that are pretty useful. We looked at our reference implementations. I encourage you to sort of go click around, explore the code. We have a blog post about GPT-J, which sort of goes in a little bit more detail about GPT-J. We have a blog post about training large language models, which sort of specifically has a demo of running GPT-3 XL. It's pretty helpful. And finally, our documentation website is also pretty helpful. It has tutorials and best practices about using the CS2. And that's it. Thank you for listening. And please let me know if you have any questions.
Question for those participating today. If you have questions or feedback on what was presented today, but also on anything else Cerebras related, please feel free to use this as an opportunity to communicate to us. In just a little bit over 2 weeks, we will have our next developer community meeting, and it'll be more SDK related. We will deep dive into our debugger. So if that's of interest to you, be on the lookout for our invitation that'll come into your email inbox in the next few days.